Okay, analysis of raster data. So this often works on the fact that we can apply calculations between on data from two different layers. As in, we have a raster layer and another raster layer. They can exist within the same file. They can be part of the same data set. For example, if we have an aerial photograph consists of three raster layers, the red, the green, and the blue, we can actually do calculations between the pixel values at each cell or pixel there. Or alternatively, we can apply values from a completely different raster layer, or we can apply an individual value over the entire raster layer. We can also apply logical functions to raster cell values. So there are many different ways of working here. Let's just quickly look at some of those, and we'll begin by looking at something that's very commonly used, and that's the mask. So here we have a mask. The mask consists of some cells that have a value of 1, they're the positive cells, they're the ones we are interested in, and some cells that have a value of 0. They're the cells that we're not interested in, the ones we want to exclude. But how do we get here? If we go back to our soil map, here is our soil map here, and I am saying in this soil map that cells with a value of 4 are clay. So soil type. Cells with a value of 3 are sand. Cells with a value of 2 are till, brown. Cells with a value of 1 are rock. So they're different soil types. Rock, you may question whether it's a soil type, but it is represented on soil maps at least, where there is no soil, or the soil depth is too shallow to be represented as soil. Therefore, you just have the rock there, the bedrock. So we have soil types here, and we then reclass this data. We then say whatever is a 4 becomes a 1. Everything else becomes 0. We don't care what it is. It's not a 4, therefore it becomes a 0. But whatever is 4 becomes a 1. So we reclass the entire image, and that gives us this mask. What good is this mask? How do we use it? Well, we now have a layer where every cell that is clay has a value of 1. We then go to our land use map here, where we have similar classes. Now the numbers mean something else. 1 is woodland, 2 is pasture, 3 is arable, 4 is built up. If we cell by cell multiply these, 1 times 1 is 1. 1 times 2 is 2. 0 times 2 is 0. And so this is a very trivial calculation. 1 leaves the land use map unchanged. 0 zeros it. 0 times anything is 0. This then results in a map of soils, of clay soils, and how they are used. This is the land use, so the land use data comes through. These are the cells that are clay when they're being used in this manner. So we have some woodland and some woodland on clay soil. We have some pasture on clay soil. We have some arable on clay soil. And we have some built up on clay soil, presumably something like a media market or some other uselessness for clay soils. So we've taken this map of land use of clay soils, for example, and now we can do a calculation. How many of these are actually farming pixels? How many of these are, certainly in a Swedish sense, efficient uses of clay soils? We have a very limited amount of farmland to use. We should be using it as farmland rather than building shopping centres on it, just because it's nice and flat. It's farmland. We need all the farmland we can get. So here's our analysis of our landscape. We've got 4 farming pixels and 3 non-farming pixels. So 3 of the pixels in this, or cells in this area, are actually being used incorrectly. They're not farming. So we only have a 57% use of our clay soils as farmland. The rest is being wasted being used as something else. Could be placed on other types of soil. For instance, if you want to build a shopping centre, build it on till. You're not losing anything. So, continuing with our analysis, we can return again to the idea of logic, the and the or, and we can apply these to raster as well. We can, for example, as illustrated here, we can have one raster that represents one type of data. This is essentially the mask again. Doesn't have to be, it could be something else entirely, but we can set a condition here, raster A is equal to 1 and raster B is greater than 3. Where both of those conditions are fulfilled, we get a true value, so we get the 1. This kind of eradicates the information in the B here, in this version that I'm doing, just simply as an example, and we get those areas where both of these conditions are true. As I said, this doesn't have to be ones, this could be something else entirely. This could have been raster A, could have looked like raster B, and we just wanted all those that are bigger than some other value. It doesn't matter, where both are fulfilled. And then we get this logical map. So that was one way of doing things. We can also multiply each pixel value in a individually. We can take a single value. For example, we can run over this raster here and multiply each cell by 0.3. So 151 times 0.3 gives us 45.3. Why we would do that? There are various reasons why you might want to rescale a raster, the data in the raster cells. It's just as a rescaling it in some way, the values within it, not the actual spatial extent. That's possibly something you might want to do. 0.3 was just an example. More useful, perhaps, depending on what you're trying to do, more common at least, would be something called a kernel analysis or neighborhood analysis. Typical example of that would be to calculate the mean value. So you're looking for the mean over a particular area. This is called a neighborhood analysis or a kernel. So we use those to examine a particular portion at a time of the raster. So we're looking at this area, then we move our window, we move our kernel, we move this neighborhood along one step and then redo the analysis there. Then we move it along another step and redo the analysis there. And by repeating this analysis step by step over the parent raster, we create a new raster where the values have been calculated from the parent using whatever method we've decided to use within that window. And as I said, quite often it's some form of a statistical analysis, the mean, for example, which we will look at, or we can do edge detection using slightly more advanced algorithms. So let's just look at calculating the mean. This is our window, the kernel, the neighborhood that we're going to move over this raster. So at the moment, our window is over this top left-hand corner. And I've put in here what I'm going to call a no data value, simply because I would rather actually put in -9999 there, but we don't have room in the cells. So let's just leave it at that. For this example, that's good enough. So why is that a no data value there? Well, we have a problem because our window sits here, and as we can see, we've got 5 cells. 5 of the 9 cells don't have any values in them. We can create a mean, the average value. We could just calculate it from these, but it feels like that average, that mean for that cell up there, it doesn't have the same quality as one, say, calculated in the middle, where you would have 9 cells available. So it's quite common to say, okay, well, we won't calculate the edges. We'll leave the edges out. So that one's invalid. And then that's the same all along the top. We have this problem all along the top. And in fact, we have it all down the side. All sides have this problem. So we leave out the edges, don't calculate the values along the edges because the data there wouldn't have the same quality as the data within the image. Once we move in a step here, we can calculate a value, because there are 9 valid values to put in each cell here, and we can calculate the mean. And then we can move over one step, calculate the mean for the new. And then we just go over the whole raster, and we've calculated the mean at each step, all the way over. So for the mean of all those values that are present within this window gets put there. So that's calculating the mean, neighborhood analysis, kernel analysis. We can do the same thing with the mode, for example. If we want to get rid of noise, speckles, stuff like that in our analysis, we can find the most frequent value. The mean calculated sort of trends over an area, whereas this will get rid of the small details that perhaps aren't interesting. You will end up with values that exist in the original map. The mean actually created new values, so the mean isn't very good for class data, it's better for continuous data rather than discrete, whereas the mode can actually handle discrete data, class data, because it doesn't create any new values, it just simply picks the most common value within an area. So you can have wheat rather than wheat. But I think we'll illustrate with this slide another problem. The kernels we've looked at so far have been 3 by 3, but what happens if you use, say, a 5 by 5 or a 7 by 7? Well, the problem extends. This edge problem becomes even larger, because you then have your kernel, your window, sticking out even farther, and you need to move even further into the raster before you get a perfectly valid calculation. So your edges become larger. Now this is important. The edges that you can't work with mean that you need to be aware of this when you order data, when you're defining your work area. If you're interested in a particular area, you will need to have some extra data on the outside to counter these problems where you can't do these calculations correctly. Just a little bit extra on the edges.